Okay, so last time we started our transition from looking on moments and cumulants as formal power series, or looking them as coefficients in formal power series, to a more analytic description of those series. And one of the main objects is the Cauchy transform. And we saw that this is, as a power series, it corresponds to the moments, but it has the advantage that actually it's an analytic function of all of the upper half plane. And furthermore, we can recover the corresponding measure by the status inversion formula if we go to the real axis. Okay, and now, of course, we also want to see what is with the cumulants. We put the cumulants also in the formal power series, but we also would like to give more analytic structure to this. Okay, so maybe let me just recall Cauchy transform, our probability measure. This is a function in the upper half plane, which is defined by 1 over z minus t, integrated with respect to mu over the real axis, or if we have compact support, just over the interval, in which or just over the support. And if you make a power series expansion of this, then we saw that if the support is, let's say, in the interval from minus r to plus r, then this can be written as the moments of the measure divided by z n plus 1, the sum n equal to infinity. And this is a convergent power series if z is larger than t. Okay, so if t if larger than r, if the support is contained in minus r to r. Okay, so this means this analytic function has a power series expansion about infinity, but only for some domain. So this means outside. Okay, I mean it's defined here, and here we see that actually, if we have compact support, we can also define it not just in the upper half plane, but also in the lower half plane, and from the outside of such a circle. Okay. But of course the point is, if we want to use this inversion formula, we have to go to the real axis, in particular where the support is, and of course the support is inside here. So this power series expansion does not really tell us much about how to get the measure directly. So we really have to extend somehow this power series extension to an analytic function in all of the upper half plane, in particular close to the real axis. And that's the advantage of having it as an analytic function and not just as a power series. Good. Okay, but now we also want to see the cumulants, because our goal at the moment is really to understand the free convolution. And the free convolution is about the sum of free variables. And to understand the sum of free variables, we saw it's really advantage to go over to the cumulants, because the cumulants are additive for free variables. Okay, so this means what we understand quite well with respect to the addition is the sum of the cumulants, not directly the moments. Okay, but for this inversion formula, we of course need the moments and the Cauchy transform. So we should also think how we make the transition from cumulants to moments. Okay, so for this, and the following remark. So first of all, from this power series expansion, we see that the Cauchy transform is nothing but our function m, the moment generating function, which we considered before, in disguise. So you see the Cauchy transform is a version of this function m, which we had before, this moment series. Moment series, where we just took a power in a series in powers of z to the n, and the moments with the cumulant, the moments with the coefficients. So m of z is defined as a formal power series as 1 plus summing from 1 infinity mn z to the n. Of course, formally, I mean, this is a term corresponding to n equal to 0. Of course, the zeroth moment is just an integral over everything which is mass 1, because we have a probability measure. Okay, and you see this is more or less the same as this formula. The only difference is that we don't have a set, but we have 1 over set, and then we have an extra 1 over set. So this means that this moment series, which we considered 3.6, is related to the Cauchy transform by the fact that G of Z is essentially m in 1 over Z, which will give us mn, and then divided by Z to the n, and then we have here an extra 1 over Z. So we have here extra 1 over Z. Good. Okay, and then, so how is now the relation? So we have a relation between the moment series and the cumulant series, and now let us rewrite this in terms of G. Okay, so the relation cumulant series. So this was the cumulant series. This was defined in the same way as a generating function, but not in moments, but in cumulant. So it's 1 plus the sum of 1 to infinity by n z to the n. So this is also considered in 3.6. And there we had this relation between m and c. So what was this? It was this functional relation. I take the cumulant series and I'm plugging in as the argument z times the moment series, then I'm getting the moment series. This was just reformulation of the combinatorial relation between moments and cumulants in terms of this generating series. Okay, now I want to replace m by g. Okay, so first of all, maybe I should go over instead of z. I should go over to 1 over z, so that we write this here by replacing z by 1 over z. So we have z and 1 over z. This is equal to 1 over z. So I have just replaced it. And of course, this here, this argument now, this is exactly g of z. Okay, that's quite nice. And this m of 1 over z, this is essentially g, but multiplied by z. So this here becomes g of z. So means what we have here is that if I take the cumulant series at g of z, and I'm dividing by g of z, then I'm getting z. Okay, so this tells me essentially that c of its argument divided by the argument is actually the inverse under composition of g. Okay, so maybe c of z divided by z is the crucial quantity. Maybe we call this k. K of z. If I take c of z and divide it by z, so this is essentially our series c, but shifted by 1 in the z. We divide it. So I get 1 over z plus, and then I have here a shift by 1. And then this tells me that series c and k are inverses of each other. So then, with this, we have, if I take k and I'm plugging in g, then I'm getting back z. Because k of this argument is c of this argument divided by the argument. This gives me z. So this tells me that this is the inverse of this under composition. And this means also, of course, the other way around. So this means also if I take g of k of z, I get also z. Good. Okay, and c was an ordinary power series in powers of z, in k k, we are dividing by z. So I mean, you get here a pole, you get 1 over z, but the rest is just an ordinary power series. So this means this k has a pole at 0, 1 over z, and this we are splitting off. And the rest we call r. The rest should then be a nice analytic function. So since we have z equal 1 over z, split this off and write k as 1 over z plus the rest, and the rest we call r. That's the famous R transform if we go into it. And write k of z is 1 over z plus r of z. And of course r of z is then just, okay, this gives 1 over z, and it's just this term divided by z. So it's a generating function with cumulants, but there's a shift of 1 in the power of z. Is the sum from 1 to infinity against cumulant divided by z to the n minus 1. Good. Okay, and of course, if our measure has compact support, and that's a setting we consider at the moment, then we know the moments are exponentially bounded. And this also means that the cumulants are exponentially bounded, and so this means this is a power series expansion about 0, which converges if this thing here is small enough. Okay, so this means this r of z, at least in the neighborhood of 0, is also an analytic function. So I mean, the Cauchy transform is an analytic function in the neighborhood of 0, of infinity, which means outside a big wall. So for z large enough, and the R transform is an analytic function for z small enough. Okay, but the Cauchy transform, of course, we know that we can extend it to all of the upper half plane. For the R transform, this is at the moment not clear, and that's the kind of question which we want to consider. So of course, the question might be: is it true that also the R transform can be extended to all of the upper half plane, for example? But that's not true in general. Also, the R transform is not as nice an object as the Cauchy transform, but of course it's still an important object, and it is an analytic function at least somewhere. But at the moment you only can define it as as a power series. And of course this raises the question: what should we do if we want to extend our definition of the free convolution or machinery for calculating it from measures with compact support to all measures? The Cauchy transform, of course, we know exists for all measures. The R transform, at the moment, in principle, we only know what to do with it, or it's only defined if we have compact support. But of course, the idea is that we take the equation which relates the Cauchy transform and the R transform and use this equation for defining the R transform in general. Okay, but this means we really should do some more analytic tools, and that's what we want to do in the following. Okay, but maybe let me just write here my remarks. So compact support. And in this section, we are only dealing with this equation, and the cumulants are exponentially bounded. Because the moments are exponentially bounded, it is the same as the cumulants being exponentially bounded. And then this power series here really converges for if z is small enough. And power series converges for absolute value of z sufficiently small. Okay, but of course the analytic nature of the R transform, I mean, can be extended to somewhere, and can be also maybe define it from the equation. That's something which we want to treat next. Okay. And so I'm collecting those things in the next theorem. And this is, I mean, in this compact case where we have the power series expansions, I mean, there it's things are somehow easy, maybe the power series. But still, I want to show you how we do it in an analytic way, you know, how we can deal with this equation in an analytic way. Because if in the next section we want to go over to all probability measures, then there is no other way of doing it. And then you have to do similar things. I mean, maybe technically they are a bit more complicated, but in principle it can be done. Okay, so I don't want to do all the technical complicated things in the next chapter, but I want to give you an idea in this chapter how one can do it in a maybe simpler case and so on. But I mean, up to now, essentially we considered, we talked about power series, and now we really going to use more analytic tools for complex analysis for understanding and dealing with those objects. Okay, so let me write down the theorem. So this goes back to Voiculescu. This is for the compact case. I mean, this was the free convolution. That was one of the first questions which Voiculescu answered about free probability theory. One of the first questions he asked and also answered by essentially developing this machine object. So this is theorem. Voiculescu, 26, and maybe in a form, I'm doing it here, the arguments, they were later done by Bercovici and Voiculescu a few years later, maybe a bit more analytic, complex analysis. So there's a later paper by Voiculescu and Bercovici from 1992, and that's maybe more the proof I'm going to use for this. Good. Okay, so the first point, I mean the main point is about defining the R transform. So if I have a measure, I have the Cauchy transform, and what I want is the R transform, but really defining it not by power series expansion in terms of cumulants, but really by looking on this equation. So this equation gives me the relation between the Cauchy transform and the K transform. K is 1 over z plus the R transform. So the question is, I mean, if I know the Cauchy transform, can I use this equation for defining the R transform? And this is really uniquely defined. Where can I define it? By this equation. Okay. The setting is the repeating measure. And we assume it has compact support. And as before, we assume that the support is contained in the interval from minus R to plus R. Contained in interval minus R plus R. And then we, of course, have the Cauchy transform. Consider Cauchy transform. So G mu, but at the moment I only have one mu, so I just call it G. And I consider it as an analytic function. Okay, and at the moment, I really want to restrict it to a domain where I really can be sure that I'm able to take inverse. Because I mean, what I have to do here, the K, if I have G, the K should be the inverse of this function. Okay, but of course, I mean, Cauchy transform is defined in one of the upper half plane, but it doesn't have to be injective function everywhere there. So I should restrict to a domain where I can be sure that it is at least injective. Okay. And actually, in a compact support, I know that I can define it outside of balls, not just restricted to the upper half plane, but also I can go to the lower half plane if I'm staying outside the ball. So I'm looking now on G as a function on Z, which are outside a big enough ball. And the power series expansion, you know, I mean, this converges if we are bigger than R. But now I'm going 4 times bigger, so I'm going outside of 4R, because there I can control it better. And then I'm going to the complex plane, where I can also control where I am. Maybe I'm going to a ball of radius 3R. So I mean the Cauchy transform maps neighborhood of infinity to neighborhood of 0. So big sets are mapped to small sets. Because the leading order of the Cauchy transform is 1 over set. Okay, so this means what I have here, picture. So I mean I have here something, and maybe I call this U here, this set. So I have here, let's say, the exterior of a ball of radius 4R. Okay, I take the outside of this, and this under G is mapped to something which is sitting inside a ball of radius 1 over 3R. That's what I'm saying here. Okay, so this thing here is G of U, and here I have a radius 1 over 3R. And my statement is that on this restricted to the exterior of this ball, G is an injective mapping. Okay, so everything here is mapped to here, and it's injective. That's the main statement which we have to see. Then G is injective on this set U, and actually G of U, so I mean G of U is the thing where I might want to invert by mapping, but actually again I prefer to invert things on balls, so I mean I should also find a ball which is sitting inside here. And so we also show that there is a ball of size 1 over 6R which is contained in this. So here I have the radius 1 over 6R. Then of course the mapping from here to here is also injective here, so I can invert the mapping on this ball. And that will be where I will define this. Okay, so G of U, and G of U contains a ball, which I call, let me call it V. So this ball, that is V. Contains V, which are complex numbers. Value is less than 1 over 6R. Okay, and this means I can invert the Cauchy transform on this V, and of course that's what we are calling K. Hence, inverse on V. So this is G to the minus 1. That's what I call K. And this goes from V to U. So this goes from the inside of the ball of radius 1 over 6R to the outside of the ball of radius 4R. And this is a well-defined mapping. And of course this K, if I'm looking as a power series, I mean G has the behavior of leading order 1 over set, So the inverse also has leading order 1 over z. So this k has a pole, as we also have seen before. And so this k has a pole, and I'm separating off this pole, and the rest I call r. And this is that analytic function. K has a pole, 0. K of z is 1 over z, that's r of z. And this r of z is now also something which is defined on V, and it is an analytic function there. Okay, so r, maybe if I want to indicate that this is the R transform of mu, then I also write r mu. This is a mapping from V. Maybe I'm not specifying exactly where it goes to, because this 1 over z, I mean I know exactly where k goes to, but this 1 over z maybe perturbs things a bit, so I don't care so much about it. Okay, so is this being analytic? Okay, and then of course we have that k and g are inverses of each other, so we have exactly those equations there. If we choose the set small or big enough. So what we have is that g of k is equal to z, but k of course is f of z plus 1 over z. This is equal to z as soon as I can be sure that this guy here falls into the domain where I have made those statements. So if this falls into this domain outside of 4R, right? This can be. This is true if I'm in this set V. So 4z less than 1 over 6r, because it's defined obviously as the inverse. Okay, but I also have it the other way around. So here I have, if I make set small enough, then this here is big enough, such that I can apply g to it. And the other way around, of course, the other way around says that this. If I plug in this function here, g has an argument, then I also get z. So I take r, plugging in g as an argument, plus 1 over z, but the argument is now g. So this here is also equal to z. But here I have to make, of course, z big enough, such that g of z falls into the domain where this r is defined. So I must fall into this domain V, and this I can ensure. For example, if z is larger than, let's say, 7. I mean, the precise nature of all those numbers is not really important. It's just saying, if z is small enough or z is big enough. But I mean, you can really make it concrete. For concrete estimates, it's good to have concrete numbers. Good. Okay, so that's the first part. That's the main part. This is really defining the R transform essentially as a solution of this equation. And also getting from this that you have an analytic object. And of course, in our context here, this analytic object must be the same as before, so it has a power series expansion, and the coefficients of these expansions are the cumulants. Okay, so that's the second part. Big theorem, we have some space left for you to prove. So this was only part 1. So part 2. So R S on V, okay, that's where we find it. Power series expansion. Power series where the coefficients are determinants. And it's set like this shift of 1. Going from infinity. And on B means if z is less than 1 over 6r. And of free cumulants of the measure mu. Free cumulants of the moments of the measure mu. Cumulants of the moments of the measure. Good, so that's part 2. I mean, that's just saying that it fits together with the more combinatorial things which we did before, but now we have a more analytic description of R. And now part 3 is really the main use of the R transform. Namely, that if I'm looking on the sum, or the free convolution of two measures, then I mean the R transform linearizes this. So the R transform of free convolution is the sum of free variables is the sum of the R transforms. That's why we introduced those cumulants. So if I have now two measures, in our frame they should be compactly supported. Compactly supported probability measures. Then we have that the R transform of the free convolution mu plus mu at Z is the R transform of mu at Z plus the R transform of mu at Z. And this is true, at least for sufficiently small set. I mean, this is in principle true where all of those three things are defined. Okay, but I mean, the definition depends on the support. Okay, so of course, if I know the support here and I know the support here, I also have an estimate for the support here, so we could be precise, but I think it's not really important. So I'm just saying for sufficiently small absolute values of set. Good. Okay, so we have to prove these are the main point is of course part 1. We really think about the definition. And of course in definition, I mean G is a mapping going from the neighborhood of infinity to 0. And I mean neighborhoods of infinity is a bit maybe not so nice. I mean it's maybe nicer to talk about insides of ball than instead of outside of balls. So we just go over from set to 1 over set. So I just consider the function the G of 1 over set, which of course maps infinity to 0, and then I have a function which is defined on a neighborhood of 0. And then we do all the arguments in terms of this, and then at some point we go back to G, replacing set by 1 over set. Okay, so this means let us first define, or maybe this is the R transform. It's so important that we also give officially the name to it. So maybe before I start the proof, let me make the definition that this transform R, which appears here, is called the R transform. Here's the definition. So R mu as you see, I mean, the analytic properties of the R transform are not as nice or clear as the analytic properties of the Cauchy transform. Which means that in the next chapter, actually, we will also talk about alternative to the R transform. Okay, for now, it's all about the R transform. So, let us start the proof. Okay, so first of all, as I said, we go over from set to 1 over set. So to go away from infinity, to move this to 0, so I define a function f of z, which is g of 1 over z. And then I'm just talking about this function. Okay, and of course this has a power series expansion. Then power series expansion, and it's just the expansion of G, but now we're written in terms of 1 over z. So f of z is the sum N in its moment times z to the n plus 1, n starting at 0. Okay. And where does this converge? This of course converges inside the wall of radius 1 over r. I mean G converges outside the wall of radius r, and now if I replace z by 1 over z, I'm mapping the outside to the inside of the wall of radius 1 over r. So this converges outside or inside now from 1 over r. Okay. And now, of course, we are claiming essentially that this f here is invertible. Not inside this wall, but inside the wall which corresponds to this here. So this means instead of now looking on G, I replace this here by a wall of radius 1 over 4r, but then I'm looking on the inside. And maybe this one's u, and this essentially is the u that we call it u to the minus 1. It's 1 over the guys which I had here. And f maps this here. I mean, this here, this relation between this is just a set by 1 over z. So there's nothing really here. It's just it's changing inside and outside the words. Okay, now I'm arguing here that essentially this guy here, I mean this is mapped to something here. And we want to see it's injected there, and we also want to see that we have a smaller wall inside this image, so that I can invert this value here. Okay, so maybe first let us check that the image really is contained in this big ball here of radius 1 over 3r. If I restrict my set to lie inside this ball. This is just a power series estimates, so still not really doing complex analysis, but just still playing around with the power series. But they tell us where we should go. Okay, so if I take z less than 1 over 4r, we have, I'm going to estimate the absolute value of z. I use just this power series expansion. So this is less or equal to the sum, and it equals 0. I have the absolute value of the nth moment, and I have absolute value of z to the power n plus 1. And of course we know the moments are, if the support is less than r, they are drawing at least at most with r to the n. So there is the moment, it's bounded by r to the n. And z, of course, I have restricted to this. So this guy here is less than 1 over 4 to the r to the power n plus 1. And so you see, of course, essentially I can estimate this in geometric series. So I have here things to the power n plus 1, and here I have it to the power n. So I take out one factor from here, so 1 over 4r, and then I'm left with the sum over, I have here 1 over 4r, and I have here r. So the r goes away, and I have just 1 over 4 to the power n. Okay, this of course is 1 over 1 minus 1 over 4, which is 1 over 3 over 4, which is 4 over 3. And you see this 4 goes away, and then left is 1 over 3r. This is the radius which I gave here. Okay, so all the f of z which you get from here are inside this wall, because the absolute value is less than 1 over 3r. Good. Okay, so that was just a power series argument, but now we really want to see that things are injected. Okay, if you have a power series, it's hard to see that this is injected or not. So now we really have to do a bit more analysis. So what I want to do is, I now have to take 2 points here, and I have to see that the image here, if the points are different, then the image should also be different. Okay, so this, and I can do this by estimating essentially the differential quotient of this situation that I can find a bound from below. Because then the f's cannot become 0 if the sets are not becoming 0. Okay, so what I want is more space on the blackboard, but okay, not getting this, so we continue here. Good, so what I want to do, let's say I have set 1 and set 2, let's say different points here, and I want to see what happens here on this side. And for this, I will look at the difference quotient. So I take f of set 1 minus f of set 2 divided by set 1 minus set 2. What I want to do is to find a lower bound for this. Because if I see that this thing in my wall, for any choice of set 1 and set 2, can be estimated by some number which is strictly greater than 0, then of course this means if those guys are different, they must also be different. This then gives me objectivity. Okay, and this I'm estimating. I have the difference quotient. Of course, I want to connect it with the derivative of the function, but I also need estimates, so I should go over maybe to the real situation. So the absolute value I'm estimating by the real part of corresponding difference quotient, same difference quotient, z1 minus z2, and the difference quotient I can get by integrating over the derivative of my function. So this here is the same as the integral, let's say from 0 to 1. When I'm running from z1 to z2, I take the real part, of course the real part of the integral use, and here I take f prime of z1 plus t times z2 minus z1, integrating with respect to dt. So that's just fundamental theorem of calculus. So integrating the derivative, I get the functions. So I'm just writing this difference quotient as the integral over this. Okay, this tells me if I want to have an estimate for this, it would be good to find an estimate for the derivative of f prime, and here I'm integrating over the straight line connecting z1 and z2. So this means I'm z1 and z2 are somewhere in this wall, and I'm integrating over the line, so I'm just integrating over points which are also inside the wall. So I should find an estimate for the derivative inside this wall, which is bounded, an estimate, I want to estimate it from below by something which is strictly bigger than 0. Okay, so let us see how we can do this. Okay, so now I'm taking this derivative at a point z, but this point z should be in my wall into the minus 1. So I'm taking z, which is less than 1 over 4. And for this, I'm taking the real part, f prime of z. So this is the real part. And what is f prime? I'm in a wall where I still can use my power series expansion. So I have the power series expansion, which I just erased, where the coefficients of f are the moments, and then of course if I take the derivative, I just get have to take the derivative of z to the m, so I get m times z to the m minus 1. So what I get here is 1 plus 2 m1 z plus 3 squared plus 4m3 z to the power 3 and so on. I mean, the power series expansion was of course without those, and then I had m1 z squared plus m2 z to the power 3 because there was a shift of 1. Okay, so the coefficient of mn was set to the n plus 1. Okay, so if I take a derivative, I'm getting this here, and this I want to estimate. So I want to estimate this from below. I want to see that this is bigger than something which hopefully is bigger than 0. So I write this here. I have this 1. Okay, the real part of this, I mean, the worst effect this can have is I have minus sign here, and I have minus 2 and 1 times z. Here minus 3 and 2 z squared, and so on. Okay, that's the worst what can happen. Now we have here really the real part is really the negative. And now of course we have estimates for those guys. I mean we also know the biggest they can be. So namely the m's we can estimate by r to the n. And for the z we also have assumed. We can estimate that. So this here is now bigger. And actually, you see, essentially, I have here the derivative of a geometric series with minus signs, but the constant term is missing. So I would need the one with minus sign. So I'm just adding this. So I'm writing this as 2 minus. Then I have 1 plus 2 times. Or maybe let me first write down the estimate. Also, this here is less, the m1 is less than r, and z is less than 1 over 4r. Also, the m2 is less than r squared, and z2 is less than 1 over 4r squared, and so on. So you see what I have here, the r's go away, and I have 1 over 4, 1 over 4 to the power 2, and so on. So I have a geometric series in 1 over 4. Okay, but the constant term is missing, because this would be a minus 1, because here everything is a minus. So this means I'm writing this as 2 minus, and then I'm adding the 1 again. So this 2 minus 1 is this one here, and then the rest is just this here, which is plus 2 times 1 over 4, plus 3 times 1 over 4 squared, and so on. This inequality here is the minus sign, this inequality here. And then what I have here is now the derivative of the geometric series in 1 over 4. And this sum here is 1 over 1 minus 1 over 4, because the derivative of the square here. Okay, and this is now, so this is 1 over 3 over 4 squared, which is 16 over 9. And so I have 2 minus 16 over 9, 2 is 18 over 9, so I get 2 over 9, which is positive. So this here is really greater or equal than 2 over 9. And this means this derivative here, which I have here, is for all z over which I integrate, I can estimate it by 2 over 9 from below. And so this means that this difference quotient can be estimated for all z1 and z2 in this wall by 2 over 9. So, hence my argument, which I just erased. Hence, for all z1 and z2 in, let's say, this u to the minus 1, which means that both of them has absolute value less than, less than 1 over 4 over r. That's the situation which I did, this estimate. We have that f of z1 minus f of z2 divided by z1 minus z2 is greater or equal to 2 over 9, and I'm bringing z1 minus z2 on this side. Okay, now you see, I mean, if I now assume that f of z1 is equal to f of z2, this means that, yeah, z1 also better should be equal to z2. So that's, or maybe the other way around. If z1 is different from z2, and this here is not 0, then this can also not be 0. This means that f of z1 is also different from f of z2. And this tells me, okay, so if I have 2 points here, then the image, 2 different points, the image cannot be the same. So this tells me on this ball, this function f is injective. And of course, this means for g, that outside this ball, the function g is also injective. So this means f is injective on the sets, on this ball, where set is strictly less than 1 over 4r, or rewritten in terms of g is injective on the ball where set is outside the ball of radius 4 over r. Okay, so this is injective. So let's let me see. Yeah, but now we are also claiming, so we are injective here, and we are going somewhere in some domain, but now we are claiming that this ball sitting inside this domain. So this means on this ball we really can find exactly one pre-image of a point here under f in this ball. That's also something which we still have to prove. So in principle we still have to prove the surjectivity of function on this domain. I mean, we know of course it's injective, so it goes to some domain, but at the moment, I mean, this could be a very strange domain. We can't control it, it contains specific balls. Okay, we say it's a ball of radius 1 over 6r. So what we have to show is that I'm taking a W somewhere here now, and I'm finding a pre-image, exactly one pre-image here. Okay, exactly one no, I don't get more. No, if there would be 2 pre-images here, I mean, we know it's injective. So, good. Okay, so this can go. And again, for this is of course something again which you cannot do just by forming power series. I mean, this power series you don't see whether you have pre-images or not. So we have to use more analytic tools, and for this actually we have to use the argument principle, or maybe more precisely the theorem Cauchy, which you should have done in complex analysis, but I will inform it just. Good. Okay. So we consider W in V. So V is this ball here of radius 1 over 6r. So this means W, absolute value, is less than 1 over 6r. And what we want to show is that we have a pre-image. So we want to show exists set, let's say u to the minus 1 here, or g, this would then be something which is here. Okay, but we are arguing with f, so it should be something there, which means z should have absolute value less than 4 over r, such that if I apply f to z, I get my W. Yeah, and of course, in terms of g, this would be g of z to the minus 1. So this means for g, I'm finding, if I'm taking for g, yeah, for g, I'm finding a pre-image exactly somewhere outside of this point. Okay, and for this, I want to use the theorem of Rocher, which is a version of the argument principle from complex analysis, which allows you to compare number of zeros for two holomorphic functions if you have estimates between them. Okay, and this question, whether this is zero, I mean, you can also phrase it as saying whether fz minus w has a zero. I mean, if you want this equation, this is the same as saying that f of z minus w is equal to 0, so you have to find a set which is a zero of this. So we want to find something like this. It is the same as saying f of z minus w is a 0, consider this function in z. W is a fixed number, has a 0 in u to the minus 1. Just recall, u to the minus 1 are the sets for which the absolute value is less than 1 over 4 to the other. Okay, and we do this by complex analysis, by comparing this problem with a problem which hopefully is not so far away, namely deforming this essentially into the problem of finding 0 of z minus w, because that's easy. I mean, f of z is close to z. It's a deformation of z. So the power series of f of z starts with z. So this is maybe hopefully close enough to z, and for this problem it's easy to find the zero. So maybe we will compare this via the argument principle and complex analysis, or actually more precisely with this theorem of Rocher, to the same problem, where we're looking for the zeros of not of f of z minus w, but of z minus w as a function in z. And we are looking for zeros in the same domain. And of course, 0 of z minus w is exactly z equal to w. So this has exactly one 0. Right? This 0 also is in this domain. Right? Because w is in this ball, and this ball is smaller than this ball. So this is contained here. So I have, of this function z minus w, I have exactly a 0 here. So this is true. And it has multiplicity 1. We always have to count things with multiplicity. But of course, this has multiplicity 1. Okay, so there. And of course, this problem, later, has 1. Good. Name z equal to w. Good. Okay, and so I mean the theorem of Rocher asked us to compare the function for which we want to know the zeros with the function for which we know the zeros in such a way that on some curve the difference is smaller, can be compared with one of the functions again. Okay, so we need a curve, and for the curve we are taking just this, because then we are asking about the zeros inside of this curve. So the curve is the boundary of the region in which we are looking for zeros. We are looking for the zeros in this domain, so our curve will be the boundary of this. Okay, so the absolute value is equal to 1 over 4r. So it's a circle of radius 4 over r. And this is of course the boundary of our region in which we are looking for the series. Okay, so what we have to do now is to estimate the difference between the two functions which we have. So, and we have to estimate it on this curve gamma. So then we have set on this curve gamma. So what we need is the difference between one function, that's the function we are interested in, f of z minus w, the difference to the other function z minus w. So we have to estimate this difference, and of course the w goes away. So here, this means we just have to estimate f of z minus z. Okay, this estimate again, this we can do by power series expansion, and this z is the leading order in this here. So we get somehow hopefully quite a good estimate. Okay, so what is f of z minus z? So f of z was the power series, where we have against moment times z to the n plus 1. And in f of z we start at n equal to 0. So the first term is 1 times z, but this goes away. So the first term is gone away, and then we start here now at n equal to 1. Yeah, good. Okay, but of course we do the usual estimates. This can be estimated by r to the n and z. And for z we make the assumption its absolute value is 1 over 4r. So what we have here is n equal to 1, and I have r to the n, and for z I have 1 over 4r n plus 1. Okay, so this is a geometric series, but it starts a little bit later, so we should take out some of the terms, so that we start at the constant term. So we take out this r. So we start here at n equal to 1, so here we have r, and here we have 1 over 4r squared. 1 over 4r squared, and then I just have r to some power and 1 over 4r to the same power, and summing over all the powers. And of course r divided by 1 over 4r, the r goes away, and again it's just a geometric series for 1 over 4. Here I'm summing from 0 to infinity, maybe r divided by 4r. So the r to the k, and here 1 over 4r to k, times away. This is the geometric series again for 1/4, which is 4 over 3. And what do I have here? Yeah, so you see I have here 4 gives me 4 times 4, 1 goes away, so I get 1 over 12. And then I have an r, but here we have an r squared, so I'm left with a 1 over. So what I have here is 1 over 12 times r. Okay. But now, of course, what I need is an estimate, not against an absolute number, but I have to estimate the difference of my two functions against one of the functions. That's what the theorem of Cauchy asks for. So I have to estimate this strictly less than one of the functions, and I'm taking z minus w. So I'm claiming that this here is really strictly less than z minus w. And why is this? Yeah, because I have the situation, my w, so where's my w? My w is inside the ball of radius 1 over 6. So the w is somewhere there. So this is 1 over 6r, and the z is running on a circle of radius 1 over 4. Somewhere here. Okay, the question is how close can W and Z come together? And of course, I mean, this is just the difference in radius. Okay, so the difference is 1 over 4r and minus 1 over 6r. And this is exactly 1 over 12r. Okay, because the W is inside, I have this strict less sign. Maybe I want to have it in between. But it's important that the theorem of Cauchy to have a strict less, but that's okay. So I really have that I can estimate for all Z running over this curve gamma, this difference here of this function, in which I'm interested, and this function, which is very easy and which I understand, I can estimate this strictly against, I mean, I can choose one of the two functions and take this one against this one. And this is what I need for the theorem of Cauchy. Because then it tells me that the number of zeros of this function inside this gamma are the same as the number of zeros of this function inside this gamma. And of course for this, it is 1. Good, okay, so let me write this down. Last argument. Also you see, for this we really have now to use a little bit more harder complex analysis. But that's the power of complex analysis. And analytic functions really have a lot of very rigid properties, so if you perturb them somehow a bit or so, you can control numbers of zeros and stuff like this. And that's exactly what we are doing here. So maybe let me just recall what we have shown. So hence, all set on this curve gamma, which is the boundary of this wall of radius 1 over 4r, we have seen that the difference between f of z minus w and z minus w can be estimated strictly by the difference z minus w. This function and this function can be estimated against this function again. Okay, this is exactly what one needs for the theorem of Cauchy, which is a corollary or follows from the argument principle. And then the theorem of Cauchy tells us that under such assumptions, we know that the number of zeros first function, so this is this one, so that's the function z goes to f of z minus w, and the numbers of zeros in the domain, so inside the curve, in the interior so the curve is the boundary of some open domain, and the number of zeros in this domain is the same as the number of zeros of the other function, which is the function z goes to z minus w in the same way. Zeros cannot be created from nowhere by doing small perturbations of functions. So they should come over the boundary, but we have control over them. So nothing would happen there. Okay, and for this, of course, the number of zeros of this function in this domain is, of course, just 1 because it's z equal to w. This is exactly equal to 1. So this means this function also has one cell. This means we have a pre-image of this W. We find exactly one pre-image here. Okay, so this is a very nice complex analysis. So we're not just doing formal power series stuff, but we also use complex analysis. Okay, but this tells us we have an inverse now of our function f on this domain. So where are we in our statement, in our theorem? Now, so we have shown the injectivity, and now we also have seen that on this ball, this is contained here. So we have a pre-image there. So now we are here that we already can say we have an inverse. And of course the inverse of the analytic function is again analytic. That's also a statement for complex analysis. So once we have analytic inverse for f. So let me call it f minus 1. And this goes from V. It goes from here. Which is this ball. Of course, it's not filling up the whole ball, but it's sitting inside this ball. Okay, now of course we want inverse for G, but G and F are related just by taking 1 over the inverse, and this means we also find an inverse for G by taking 1 over this here. So we define our K of Z as 1 divided by the inverse of F. So this gives inverse for G, which is easy to check, but later we will also see it more concretely. But maybe first let us think about the pole structure. Of course, f to the minus 1 has a simple 0 at 0. I mean, f, the leading order, f of 0 is 0. It's easy to see by the power series expansion of f, for example. So f to the minus 1 also maps 0 to 0, which means if I'm dividing here, then this guy here has a simple pole at 0. So, since minus 1 is a simple 0 at 0, a simple pole there, and I mean there are no other zeros in f to the minus 1 because we know it's injective. So this means this division cannot produce other poles. So this means this is the only problem, and the rest, if we split off this 1 over z, then we have just a nice analytic function. Since there are no other zeros of minus 1, k is of the following form. As we claim it in the theorem, it has whole 1 over z, and then the rest is a nice analytic function which we call R. K is of the form K of Z is 1 over Z plus R of Z with R is analytic on this segment. Okay, maybe we should check those relations. I mean, they are essentially saying that G and K are the inverses of each other, but this is more complex construction what we did, but we did it for f. So we should see that it really is that maybe we should see that this is the correct choice for the inverse of G. So by construction we have, if I'm on V, so this means for Z less than 1 over 6R, F and F to the minus 1 are inverses, that's what we constructed, so we have Z is F minus 1 of Z, that was our construction. F to the minus 1 is the inverse of F on this domain. So we know on this domain, this is domain B, we have this, but of course F, now we just rewrite this in terms of G and K. So F, of course, is G of 1 over the argument.
So this is G of 1 over f to the minus 1 of z. But 1 over f to the minus 1 of z is just k by definition. So this here is just G of k of z. And this also is the same as G of 1 over z as r of z. Okay. So you see that this here, and this is really the equation which we solved by our construction. We already showed that this here has an inverse on this domain. Okay. If this is the inverse of this, then it should also be the other way around. But of course we have to make sure where does it happen. Because we have to make sure that we choose arguments such that this here falls into the domain where R is defined. Then we know what to do with this. So we must then set also a little bit bigger domain. But then that's okay. So okay, maybe we have seen the theorem long enough, so maybe at least this here we have done. So instead I want to check this equation here. Okay, so let us see what we have there. Yeah, of course, f to the minus 1 is the inverse of f, so we have it the other way around, as long as we know that we are falling into the right domains. So, what we have to show is that if z is larger than z r, we have to show that g of z is then less than 1 over 6r, because that's where my r is defined, or my k. So then I can it like this. So if this is the case, then we have by the fact that f and f to the minus 1, or maybe also g and k to the minus and k are inverses, then you also have the k of g of z is equal to z. Okay, of course again, we show this for f. So permanently. Show that f of z is less than 1 over 6r whenever I'm in the domain z less than 1 over 7r. So for g, I have to be on the outside of the ball of radius 7r, and this means for f I have to be on the inside of the ball of radius 1 over 7r. Yeah. I have to show that that I'm falling into the domain of 1 over 6r, and this means r is defined there. So we only have defined r in this domain V, which is this radius. So the main point is to see that I'm using z, from which I can be sure that I'm landing in this domain. Okay, so I have to see this, and this is again a power series expansion. So we can do power series. So this follows from the estimate, z. So if I'm choosing z small enough, it's clear, z will be as small as I want, we only choose z small enough, And this is a precise way of saying how small. So this is the sum over n set to the n plus 1, summing over n, starting with 0. And this I'm estimating again. This is r to the n, and z we had said this should be less than 1 over 7 to the r, 7r. So what I have here is the sum n over to 0, r to the n, and here I have 1 over 7r to the n plus 1. And again, this is a geometric series, essentially in 1 over 7. So here I have r to the n, here I have r to the n, and then I have an extra r. And I also have an extra 1 over 7, so which I bring out. So I have here 1 over 7r. So one of those terms I'm bringing out. And then I'm just left with the sum n equal to 0, r divided by 7r to the n, which is the geometric series for 1 over 7, which gives me 1 divided by 1 minus 1 over 7, which is 6 over 7. So we have here 1 over 7, 6 over 7. 1 over this is 7 over 6. So this goes away, and I have 1 over 6r, and that's exactly what I have to see. So I'm falling inside this domain here. Okay. But of course, it's just fiddling around. I need to see how small to make it that the numbers fit. I mean, it's just to see that you can do the complete estimates, but in principle, I mean, that you can do something like this is if you just make the set here small enough, then you can also make this here small enough. But you can also give explicit numbers. Good. Okay, so that's more or less the main part is now done, and the rest is, in principle, is clear. That's just putting other things together, which you already know. Good. Okay, so let me write down part 2 and 3. So one was really the construction of the R transform from solving this equation here. To see, I mean, without knowing about cumulants or whatever, just to see that if I have a Cauchy transform, then I can define an analytic function which satisfies this equation. And this analytic function can be defined on some domain in the complex plane. And it's the unique solution of this equation. Okay, and so part 2 is now, it really fits together with the things which we have done before. But this is somehow clear. I mean, before essentially we constructed an analytic function that satisfies this relation. And it satisfies this relation from a power series, but of course this also means if I make set large enough, it's also an analytic function. Also, it's an analytic function is somewhere in the complex plane which satisfies this. But the R transform also satisfies this, so it must be the same, no? Because we have seen, I mean, there's only one solution to this, the solution which we constructed. So this other one which we have here must agree, at least for set very large, but then, I mean, analytic functions which agree somewhere, I mean, they agree everywhere. So this means this power series expansion, and actually if we have a power series expansion somewhere, then it extends to the whole wall where the function is analytic. So this power series expansion must at least be valid on this whole wall where the R transform is defined. And that's what we are saying. And from our estimates about cumulants, how the expansion growth, you would get here, I think, expansion which only is in a smaller wall. But this tells us it's also a little bit bigger wall. Okay, maybe let's. Because probably also this wall is not optimal. since we know that for sufficiently small set, the function which is given by the power series expansion by n times set to the n minus 1 solves the equation g of r of z plus 1 over z is equal to z. This must agree with our r of z, which was the unique solution of this in those domains. Must agree. With r of z. Okay. So this means in some small ball here, we know that we have this power series expansion for our function r, and power series, I mean, okay, if this is an analytic function, then it extends to the whole ball. So this means this power series expansion is at least valid in all of the ball. Since is analytic for set less than minus 6r, power series expansion must also converge there. Good. Okay. Yeah, so that's just that we have this series in terms of cumulants, and maybe the most interesting thing about the R transform is how it behaves with the free convolution. Alright, that isn't linearized. But now, I mean that we know that the coefficients are given by the free cumulants, then this is obvious. Because I mean that the free cumulants behave additively with respect to the free convolution. That's something which you have seen before, and that's coming from the fact that mixed cumulants vanish in free variables. So now, after having made the contact with power series expansion in terms of cumulants, we can use what we have seen before. So for set sufficiently small, so now we have three R transforms, and I mean they have now expansions in the corresponding cumulants. So R mu of set is the sum over kappa n of mu set to the n minus 1, so those are the cumulants of mu, then R nu offset is the sum over n's cumulant of mu offset, and R of the free convolution mu plus mu offset is the sum where the coefficients are the n's cumulant of mu plus mu set to the n minus 1. Okay, but now we know that those guys are the sum of this and this. This was essentially the proof where we showed how to define the free convolution. So I mean, there we realized mu as a distribution of some operator x, and mu as a distribution of some operator y, in a star probability space such that x and y are free. And then this mu plus mu is the distribution of the sum of x plus y. Oh, okay, but then taking the cumulant of those guys is applying the general cumulant functionals to the various variables. Oh, so then kappa n of mu plus mu is applying the cumulant functional in this probability space, in this star probability space, which contains x and y. We apply this cumulant function to x plus y. So all arguments are x plus y. And then, of course, we know cumulant functional is its linear arguments, so this just gives the sum over many cumulants, where some of the arguments are x and some of the arguments are y. And then, of course, by the vanishing of mixed cumulants, only two terms remain. So this is, of course, the term where all the arguments are x. It's a term where all the arguments are y. And then it's many terms where some arguments are x and some arguments are y, but mixed cumulants and free variables vanish, so all those terms are zero. So this means I only have those two terms. This is the nth cumulant mu, and this is the nth cumulant of mu. Yeah, and then of course, so this means this here is the sum of k kappa n mu and kappa n mu, and this means of course that this power series is the sum of this power series and this power series, and this means for sufficiently large or small set we have the additivity. Thus, sufficiently small set we have the R transform free convolution of mu and mu is the R transform of mu plus the R transform of mu. Okay, and so next time we will then see an example where we really can use this here for calculating the free convolution of something non-trivial. So maybe taking the free convolution of a Bernoulli with itself. Bernoulli is where I have mass 1/2 and minus 1 and mass 1/2 and plus 1. So what is the free convolution of this with itself? This is not obvious, but with this machinery we can just calculate it. Good. Okay.